Start chapter 4. Principle of mathematical induction. Question number 1. 1 plus 3, 3 square plus dot 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 3 exponent n minus 1, that is equal to 3 exponent n upon 1 minus 2. So we have to prove that this is true for every natural number. So first of all, we have to take this polynomial open. 1 plus 3 plus 3 square plus dot 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 3 exponent n minus 1, that is equal to 3 power n minus 1 upon 2. So first of all, we have to prove that it is true for n equal to 1. Now we have to prove that it is true for n equals to 1. So for n equal to 1, P1 equal to 3 exponent 1 minus 1 upon 2. 3 minus 1 upon 2. So 2 upon 2 is equal to 1. For first term is 1. And from the RHS, when n equals to 1 is 1. So it is true for n equal to 1. Now consider it is true for n equals to k. So pk 1 plus 3 plus 3 square plus dot 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 3 exponent k minus 1 is equal to big change n by k. So 3 exponent k minus 1 upon 2. We have to consider it is true for n equals to k. For n equals to k plus 1. Now we have to prove that it is true for n equals to k plus 1. Pk plus 1 is equal to 1 plus 3 square dot 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 3 exponent k minus 1 plus 3 exponent k. Because we have to find n equals to k plus 1. So one term is increased. So put the value of these. Use equation 2. Use equation 2. So when we use equation 2, pk plus 1 is equal to 3 exponent k minus 1 upon 2 plus 3 exponent k. Now take LCM here. 2 is LCM here. 3 exponent k minus 1 plus 2 into 3 exponent k. So 3 exponent k terms, take one side. 2 into 3 exponent k minus 1 upon 2. So now take common 3 exponent k. So 1 plus 2 equal to 3 minus 1 upon 2. So that is equal to 3 in multiplication power will be added. K minus 1 upon 2. Pk plus 1. So it is true for n equals to k plus 1. It is true for n equals to k plus 1. So it is true for n belongs to natural number. Second question, 1 cube, 2 cube, 3 cube plus dot 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 n cube is equal to n plus 1 upon 2 का whole cube whole square. So solution is, so first we consider Pn equals to principal of 1 cube, 2 cube, 3 cube dot dot n cube is equal to n plus 1 upon 2 whole cube. So first of all we have to prove that it is true for n equals to 1. For n equals to 1. P1 equals to, put the value of 1. 1 plus 1 upon 2 whole square. So 1 into 1 plus 1 2 upon 2 complete square, 2 cancel with 2. So 1 square, that is 1. For n equals to 1, the value comes 1. And from other side, for 1 times 1 cube, that is equal to 1. So it is true for n equals to 1. It is true for n equals to 1. Now consider it is true for n equals to k. So consider pk is equal to one cube plus 2 cube 3 cube plus dot 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 k cube is equal to k plus 1 upon 2 whole cube. So now this is equation 2. Now we have to prove that it is true for n equals to k plus 1. So for n equals to k plus 1, p k plus 1, 1 cube plus 2 cube plus 3 cube, dot 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 k cube. One term is major, one term is more here. K plus 1 cube. As we know, the value of this is given. Use equation 2. Use equation 2. So value of this is given. K plus 1 upon 2 का whole square plus k plus 1 whole cube. Now squaring on the bracket 2 square 4. K plus 1 whole cube. Now take common. K plus 1 square is common. K square upon 4. There are 3 power and 2 power is common. So 1 power are remain. K plus 1. Now take LCM here. 4 is LCM here. K plus 1 का whole square. 4 is LCM here. K square plus 4 multiply k multiply with 1. 4k plus 4. Take LCM here. So a square plus b square. 2 square 2 multiply k. A square plus b square plus 2ab. It is a perfect square of k plus 2. K plus 1 whole square, k plus 2 whole square upon 2 square. So now we can write it like as k plus 1 and k plus 2 upon 2 complete square. So this is true for n equals to k plus 1. As you can see, the value of n is k plus 1. K plus 1, k plus 1 plus 1, k plus 2. k plus 2 upon 2. So it is true for n equals to k plus 1. So it is true for n equals to every natural number. Our question is this: 1 plus 1 upon 1 plus 2, 1 upon 1 plus 2 plus 3. So long as 1 upon 1 plus 2 plus 3 plus dot 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 plus n, that is equal to 2n upon n plus 1. So we have to prove that. So solution is this: let Pn is equal to 1 plus 1 upon 2, 1 plus 1 upon 2 plus 3 dot dot dot, same as plus n is equal to 2n equals n plus 1. So take RHS side. Pn is equal to 2n upon n plus 1. For n equals to 1, P1 is equal to 2 multiply 1 upon 1 plus 1. 2 upon 2, that is equal to 1. For n equals to 1, it is 1 and it is also 1. So LHS is equal to RHS. So it is true for n equals to 1. Consider it is true for n equals to k. K is equal to 1 plus 1 plus 2 plus 4 1 upon 1 plus 2 plus 3 dot dot k plus k is equal to 2k upon k plus 1. This is equation 2. What is this? So consider it is true for n equals to k. Now by principle mathematical induction, we have to prove that it may be true for n equals to k plus 1. For n equals to k plus 1. For pk plus 1 is equal to, put the value of these, 1 plus 1 upon 1 plus 2 plus dot 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 1 plus 1 plus 2 plus 3 plus dot dot k plus 1 upon 1 plus 2 plus 3 dot 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 k plus 1. So the value of these is given, that is equal to 2k upon k plus 1. 2k upon k plus 1 plus this is remains 1 upon 1 plus 2 plus 3 plus dot 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 k plus 1. It is an AP series. It is an AP series. First term is A and common difference is 1. So we have to apply the summation formula. Total terms is and k plus 1 n upon 2, as you know the summation formula of Sn, n upon 2, the value of n is k plus 1 to A, the value of A is 1, n minus 1 into D, the value of D is also 1, A cancel by 1. So 2k upon k plus 1 is equal to 1 upon k plus 1 upon 2, 2 plus k. So k plus 1 is 2 comes above, 2k upon k plus 1 plus 2 upon k plus 1 k plus 2. Now k plus 1 is common from here. 1 upon k plus 1 is common. 2k upon plus 2 upon k plus 2. So take LCM, and 2 is also common. K multiply with k plus 2 plus 1 upon k plus 2. So now k square plus 2k plus 1. 2 upon k plus 1, k square plus 2k plus 1 upon k plus 2 is 2 upon k plus 1 whole square upon k plus 1 into k plus 2. So 1 is this cancelled by this. So now you can see this 2k plus 1 upon k plus 2. Now value of k is k plus 1 according to this. So it is true for n equals to k plus 1. By principal mathematical induction, it is true for n belongs to natural number. Number 4. Let Pn equals to 1 dot 3, 2, 3, 4, let dot n plus 1, n plus 2 is equal to n plus 1, n plus 2, n plus 3 upon 4. So for n equals to, take RHS, n plus 2, n plus 3 upon 4. For n equals to 1. 1 plus 1, 1 plus 2, 1 plus 3 upon 4. 1 dot 2, 1 dot 3 dot 4. 4 cancel by 4, this is 2. It is from the RHS, it is for first term, it is true. It is true for n equals to 1. Consider it is true for n equals to k. 1, 2, 3 plus 2, 3, 4 dot dot k plus 1 into k plus 2 is equal to k plus 1, k plus 2, k plus 3 upon 4. K plus 1, k plus 2, k plus 3 or 4. Question 1. Now 4 n equals to k plus 1. So this k plus 1 is equal to 1 multiply 2 multiply 3, 2 multiply 3 multiply 4 plus dot dot k multiply k plus 1, k multiply k plus 2 plus k plus 1. We are putting the value of n with k plus 1. So one term will be increased. K plus 1 change by k plus 2, k plus 2 change by k plus 3. From equation 1, we will use the value of given this. Use equation 1. This is k plus 1, k plus 2, k plus 3 upon 4 plus k plus 1, k plus 2, k plus 3. So this is common. K plus 1, k plus 2, k plus 3 is common. K plus 1, k plus 2, k plus 3 is common. So now k upon 4 remains from here and 1 is remains from here. Take LCM. K plus 1, k plus 2, k plus 3, k plus 4 upon 4. So now you can see here at the place of k, k plus 1 is here. N plus 1, k plus 2. N plus 2, k plus 1 plus 2, k plus 3, k plus 1 plus 3, k plus 4 upon 4. So it is true for n equals to n equals to k plus 1. So it is true for every natural number. It is true for and belongs to natural number.